All right, into chapter 2. This is where we'll really start getting into the physics, describing events, interactions between particles and different objects. Chapter 1 was just some preliminary thing that we'll need to use along the way, but it's not really the physics. So chapter 2 and chapter 3, as it says at the bottom, are part of what we would call how we describe motion, and there's a special word we use for that in physics called kinematics. So once we get beyond that, we'll be doing something called dynamics, and I'll talk about that later. In this chapter, we are going to talk about the concepts of displacement, velocity, and acceleration, but only in the case where things are moving in one dimension. In other words, we're going to think of something moving horizontally along the x-axis or maybe vertically along the y-axis, but they're not moving along an arc in 2 dimensions or flying around in 3 dimensions. And once we have the concepts of displacement, velocity, and acceleration, we're going to sort of specialize to the case of what if something is moving with constant acceleration. We'll find out what acceleration means along the x-axis, and we can describe the motion very precisely in those cases and answer lots of different questions about it. Okay, so let's start out with the concept of, or at least what we'll need to describe displacement. We'll describe what displacement is in a second. But before that, imagine there's a fly buzzing around in this room, and at 9 a.m. I note exactly in the room where the fly is, and I want to communicate that with you via email. How can I possibly do this and be precise about it? And the answer that you're probably used to from your math classes is pretty clear. You define what's called a Cartesian coordinate system. Sometimes this, I think I got this from Giancarlo, he may call it a frame of reference, or a coordinate frame. Doesn't matter which words you use, but we're going to put axes in my room. So I might say, oh, you know the corner where you go into the kitchen, that's right here. And if you're going along the east wall heading north, that's what the x-axis is in that corner. And if you go vertically up from that corner by the kitchen, that's the y-axis, and so on. And once I have those coordinate axes, it's easier for me to specify where it is. Now, it's good to keep in mind that there aren't any real axes in the world. So that really means that I can place my axes, the origin of my axes, wherever I want in a problem. I can always choose it. And sometimes certain choices will make the algebra or calculations easier. So we'll talk about that as we go on. And I can also give the axes any orientation I want in principle, but some orientations we'll find out can make our work a lot easier. Some of them make it more difficult. So that's a skill we'll have to learn as we go on. But once I've got the axes, as long as we know the meaning of the coordinate system, all I have to do is give you the axes coordinates. Oh, the fly was at x equals 5.2 meters, y equals 3.7 meters, and so on. And you would know exactly what I'm talking about as long as you understood the coordinate system. So chapter 2, we're going to be describing one-dimensional motion only, so we're only going to have an x-axis, or occasionally, for whatever reason, when things are moving vertically, we tend to call it the y-axis. But there's only going to be one axis that we're talking about, and we're imagining something moving along a straight line axis, like a train on a long straight track. It could go forward or backwards, but it can't turn. Let's start out with a preliminary question. An ant is walking on the x-axis. It starts at the origin, walks to the 1 meter mark on the x-axis, and then it turns around and walks back to the 0.5 meter mark, halfway back to where it started. During the time described, how far did the ant move? And, if we were in class doing this, I would have you hold up what I call voting cards, and you would vote A, B, C, D, or E. 0 meters, a half meter, 1 meter, 1.5 meters, or 2 meters. So think about how you would answer this. And now the correct answer is, well, there is no correct answer. Usually in these voting questions there is a correct answer, but in this case it's purposefully ambiguous. You might say, well, when we say how far did the ant move, there are really 2 different reasonable ways to interpret that. One way to interpret it is just to say, well, it started out at x equals 0, and it ended up at x equals 0.5 meters. So it moved a half a meter. That's answer B. The second reasonable way to interpret it was the ant moved 1 meter to go to the 1 meter mark, and then it moves an additional half meter to go back to the 0.5 meter mark. When I add those together, I get 1.5 meters. And so these correspond to two different notions of how far something moved that we're going to tease out right now. Okay? Let's suppose, just like in that ant example, that during a certain time interval, which we'll call delta t, an object moves on the x-axis from position x0 to position x1. So x0 and x1 just represent some values like 0 meters and 0.5 meters. We're going to tease out the difference between those two concepts. One is called the x displacement, we'll call that delta x, and one is called the distance traveled. So the x displacement of the object, like the ant, is just the difference between the ending position and the beginning position. So this displacement would correspond to the answer 0.5 meters in the previous voting question. Whereas the distance traveled by the object just means you look how far it travels. Don't worry about plus signs or minus signs. Just add up every time something moves by a certain distance, you add that with a plus sign to all the other distances it moves. And that's called the distance traveled. It won't be as important for us in physics, so we don't have a symbol for it like delta x, but that's the words we use for it. All right, let's try to contrast these. An object moves from one point on the x-axis to another. After it arrives at its destination, how is the displacement related to the distance traveled? So we get a lot of choices here. Greater than or equal to, always greater than, always equal to, smaller than or equal to, so on. So think about how you would answer that. The displacement is the one where we just subtract the final from the initial, subtract the initial from the final position. And the distance traveled is where we add all distance moved up positively. All right, hopefully you've had a chance to vote. And in this case, the answer is the displacement is always the smaller of the two. It can be equal to the distance traveled in the case where something is moving along the x-axis and it only travels in the positive x direction. It never moves back in the negative x direction. Then if you go from 1 meter to 3 meters, you would say your displacement is 2 meters on the x-axis, but you also traveled 2 meters of distance. So it could be equal to, but generally the displacement is smaller. If I go from x equals 0 to x equals 1 and then back to x equals 0.5, the displacement is a half meter, whereas the distance traveled is 1.5, as we saw in the previous voting question. All right, that was about displacement, and displacement was just one of those definitions, but contrasting it with distance traveled. Now we're going to define something called the velocity, which corresponds intuitively to how fast an object is going in combination with knowing the direction in which it's moving. Okay, here's the definitions that we just used up at the top. I sort of grayed them out a little bit because we're going to go and add on to them. Something called the average x velocity of the object during a time interval delta t. So we're talking about delta t, maybe it's from 0 seconds to 3 seconds. During that time interval, the object's average x velocity is just gotten by the displacement it went through divided by the amount of time that's elapsed, delta x over delta t. That's called the average x velocity. It's an average because in a certain amount of time you might have been going faster at the beginning and slower later. So this just gives you one number, which kind of averages the whole time interval. The average speed of the object is just the other thing in the numerator, the distance traveled divided by delta t. Okay, and let's contrast those two. So you can have the average x velocity and the average speed are generally different, just like the displacement and the distance traveled generally differ. Let's check out this voting question. You go on a trip along a long straight road, which we'll call the x-axis, from your home, which is at x equals 0, to the store at x equals 1,500 meters, and then you go back home to x equals 0. The entire round trip takes 1,000 seconds. What is your average x velocity during the time interval described from starting at home to ending at home? 0 meters per second, 1, 1.5, 2, or 3. If you understand what the definition of average x velocity, the answer is easy to compute because average x velocity is just displacement divided by time. And in this case, you started at x equals 0 and you ended back at x equals 0. So your displacement is 0, and therefore the displacement divided by time is 0 divided by 1,000 seconds, which is 0 meters per second. So your average x velocity, it sounds a little bit strange, like we're not getting our money's worth here. I did a lot of effort, but my average x velocity is 0 meters per second. But all it means is that, I was going one direction for half the time, and then I went in the opposite direction, so they, in some sense, cancel each other out when we take the average. Another question that we might ask is, what is your average speed during this time? Even though my average x velocity was 0, my average speed might not be 0. How do I do that? Well, I need the total distance I traveled. I went 1,500 meters to the store and then 1,500 meters back home. So I traveled a total distance traveled of 3,000 meters. It took 1,000 seconds. So 3,000 divided by 1,000 gives an average speed of 3 meters per second. So that's a different question that we're asking there. It's got a different answer. Okay, let's talk about a graphical interpretation of the average x velocity. What I've done here is imagine that something is moving on the x-axis, so it's only moving in one direction, along a straight line. And at every time, t equals 1 second, 2 seconds, 3 seconds along the time axis here, I've plotted on the vertical axis what x it was at. And I've therefore gotten what we call a graph of the motion. It looks like something's moving in 2 dimensions here, but it's actually only moving along the x direction, because at every time there's, every time there's only one x value that it corresponds to, okay? So this is a graph of something moving only on the x-axis, and I've plotted its position as a function of time for a wide range of times. Let's suppose I wanted to calculate what its average x velocity is between times t0 and t1. Well, we know that that is equal to the displacement it undergoes divided by the amount of time that elapses during that period of time. So if I look at the points on the graph and I connect them with a line, so I put a point on the graph at time t0, put another point at the ending time t1, and connect them with a line, that line that connects 2 points on a graph is called a secant line. And if I go from the one point on the one endpoint on the secant line to the other endpoint, first along the x-axis direction, which is vertical in this graph, and then along the t-axis direction, notice that delta t is this horizontal direction here, and delta x is the vertical distance, right? This is, I went from this x down here up to this x up here. So this is delta x, and this is delta t. And the average x velocity is just the ratio of those two. And notice the ratio is the rise over the run, if you're familiar with that terminology, for the secant line. So another way of saying it is the average x velocity is the slope of the secant line between the two times for which you're calculating that average x velocity. Okay, so slopes of secant lines between 2 points correspond to average x velocities. You got to remember, this is the way this graph is drawn here. This is what we call a positive slope. A negative slope would go down like this, right? That would be a negative slope secant line, and 0 slope is completely flat, right? More positive would go up at a greater rate like that. Okay, now nobody cares about the average x velocity. We're just using that as a stepping stone to what physicists really care about, which is the velocity. I would like to know, maybe at time t0, given this graph of motion, at time t0, how fast and in what direction was I going right at t0? I don't want to know the average between t0 and t1. And that idea, how fast you're going and in which direction, is given by not the average x velocity between two times, but the x velocity, sometimes called the instantaneous x velocity, but you don't have to say instantaneous, of the object at a single time. And so when we come back, I don't try not to make the videos too long so they're easy to break up into sections. And when we come back, we're going to introduce the notion of the x velocity, or the instantaneous x velocity, when we get back. So let's take a quick break and come back and watch the next video when you get a chance.